It's quite lengthy, so please bear with me. It'll be quite a while. I won't go through every detail of it because it's quite a lot, but I want to at least give you an overview of most of it. And then if there are any questions, do ask, and I'll certainly take examples if you want me to as well. Okay, so let's start the slideshow. Okay, so this chapter 2, is about functions and graphs. And remember, we're hoping to cover chapters 1 to 4 before summer. So it incorporates something called the modulus function. And we'll see that the modulus basically takes the positive value of something. And we need to be able to draw it and solve equations of this kind. You need to know about language, such as mappings, functions, domain, range. You need to be able to compose functions, which basically means put the output of one function as an input into the next function. So here, x goes into g and then it goes into f. And in B, x goes into f and then into g. And you have to make sure you get these the right way around. And then we look at inverse functions. You may have done these at GCSE, but we will look at how to do them in cases like this one, where you can't simply undo each of the operations of your function in reverse as easily as you might have done in the past. And then we look at transformations where you have a function which may or may not be linear. You take the modulus of it, or slightly trickier, where you have the function of the modulus of the input. So all of that is covered in this chapter. Okay, so first of all, what is the modulus of a number? So the modulus of a positive number like 6 is just 6. The modulus of a negative number like -6 is still 6. So the modulus of -7.1 is 7.1. And as it says here, modulus is often used for difference. So if you want to know the difference between 7 and 4, the difference is 3. Now, if you did 7 minus 4, you get 3. If you did 4 minus 7, you get -3. But either way round, if you took the modulus of one minus the other, you'd have the size or length or distance, which is what modulus finds. Okay, and we use modulus not only for numbers and functions, but also for vectors to mean length. So here's a function, and let's look at what it is. What it says is that you take an input value x, and remember x could be anything, then we multiply it by 2, then we subtract 3, then we take the modulus of that result, and then we add 1. So what happens if we take those numbers? Just have a look. Well, if we take 5, we take 2 times 5 is 10, minus 3 is 7, the modulus of 7 is still 7, plus 1 is 8. Now if we take a negative number like -2, 2 times -2 is -4, -3 is -7, but the modulus of -7 is 7. So that gives us 7 plus 1 is 8. So in this case, we would have the output of 5 and -2 are the same. Whereas if you didn't have the modulus, the function f of 5 would go to 8, but -2 would not go to 8. Putting 1 in, we have 2 times 1 is 2, minus 3 is -1. The modulus of -1 is 1, plus 1 is 2. So hopefully you can see, you can work out the modulus of particular values by just taking the positive value at the stage at which the modulus applies. So modulus of x, how can we do that? Well, GCSE style, what we can do is we can create an xy table. For inputs x, we can plot the y's. So what's the modulus of 0? Well, it's just 0. What's the modulus of 1? It's just 1. What's the modulus of 2? 2, and so on. What's the modulus of -1? Well, because it gets the positive value, that will give us 1. What's the modulus of -2? It's 2. So y equals modulus of x looks very much like y equals x when x is positive, but it looks like y equals minus x when x is negative to bring the x back to being positive. Yes? Okay, so that's the modulus of x. And to sketch in general the modulus of ax plus b, you would sketch y equals x plus b, and any parts that are above the x-axis you leave, any parts that go below the x-axis you reflect to go back above to make the positive. Okay. I quite like to draw them separately and to write the equation of each of these lines. So what I would do is for this part of my modulus function, I would write y equals x. And for this part of my modulus function, I would write y equals minus x. Remembering I can't use y equals x for values of x on this side, and I can't use y equals minus x for values on this side. I have to restrict which formula I use for which values. Okay, let's carry on. So sketch y equals the modulus of 2x minus 3. How do we do that? Well, they've drawn it for us. What I would say is, when is modulus of 2x minus 3 equal to 0? It's equal to 0 when 2x equals 3, which means that when x is 3 halves. And then when x is bigger than that, we'll just have y equals 2x minus 3. So I would label this line y equals 2x minus 3. But where y equals 2x minus 3 goes below the x-axis, it gets reflected, and I would label this line here as y equals the negative of 2x minus 3, which would be y equals minus 2x plus 3. Okay. So now suppose we want to solve y equals modulus of 2x minus 3 equals 5. If you did it by a diagram, which is a good idea, you would draw y equals 5, and you would then look to see when do they have the same output. And they have the same output when this part of the modulus function crosses y equals 5, and when this part of the modulus function crosses y equals 5. So we solve simultaneous equations, but for the one on the right, we have to solve y equals 2x minus 3 equals 5, which gives you x equals 4. And for one on the left, you have to solve minus 2x minus minus 3, which is minus 2x plus 3 equal to 5. Okay, this is one of the reasons I like to label each of these lines separately, so then I know its equation without having to worry about what it might be. And then notice that when we get the solution on the right is a positive value of x, and the solution on the left is a negative value of x. If those were not consistent, there would be a problem. And we can carry on doing other problems, okay? So with this one, we sketch y equals 2 minus a half x, which is just a straight line. But for y equals the modulus of 3x minus 5, we draw y equals 3x minus 5 down to this point here. And then to the left, we draw the negative of 3x minus 5, which is minus 3x plus 5. And so if you want to work out these 2 points where the line crosses, then we get 3x minus 5 equals 2 minus a half x for this one here. And for the one on the left, we have the negative of 3x minus 5, which is 5 minus 3x, equal to 2 minus a half x. You solve them and you get your two values. And if you want to know when 3x minus 5 modulus is greater than 2 minus a half x, first of all, you work out when they're equal, and then you say, we want to know when the modulus function is greater than, it means when is the y coordinate of that graph above the y coordinate of this graph. And so we can see the modulus function is above the straight line when x is less than 6/5 or when x is greater than 2. Okay, so you solve inequalities much the same way as you solve equalities, but you have an extra step at the end where, having found these critical points where they're equal, you then try to work out which side or sides you have the inequality. Okay, and so this is just more practice. I'll skip over that because that's just more practice and you can look at that later. So exercise 2A you should be able to do after that. So what's a mapping? A mapping is something which maps input values to output values. And so you can see drawn in an ellipse here, you've got your input set, which is called the domain, and your output set, which is called the range. And a mapping, all it does is it takes values from the input set to the output set. Okay. Now, the mapping could be anything arbitrary, which means that you could have no real rule. So 0 could map to 4.4 and 7.2, 2 could map to 1, -1 might not map to anything, and -1 might not be mapped to from anything either. Okay, or you can have a rule. X goes to 2x basically means that any value goes to twice its value. And they're all mappings. Also notice one input might map to 2 multiple outputs. Okay, that would be a one-to-many mapping. One value maps to more than one value. We don't say 1 to 2, we say 1 to many, and it doesn't have to map all the points to 2 or more. If any one of the points maps to 2 or more, then it's a one-to-many mapping. Or you can have values that don't have an output, or you could have values that are not mapped to. All of that is possible with mappings. The domain is a set of input values, as I said, and the range is a set of possible output values. Okay, so what is a function? As it says here, a function is a mapping, so it takes input values to output values, and this is the important bit, such that every element of the domain is mapped to exactly one element of the range. So there are two ideas here. The first is that every element in the domain has to be mapped somewhere. You can't say, I can't cope with this number. If that happens, then the mapping you have is not a function. And the second thing is that each of those input values maps to exactly one value on the output set. Okay, you can't have one input value going to 3 or 2 output values. However, you can have 2 output values being mapped from the same input value. Okay, but each of those input values went to a output value. So be very careful about this definition, okay, to understand it well. So here we have a notation. For example, this notation is saying that f of x is 2x plus 1 means just the same as this notation, which says f takes the input value x to the output value 2x plus 1. Okay, and we can consider graphs as essentially having 2 coordinates, an x and y coordinate. And so the x coordinate is your input value. So here I've got an input value. And then by using the graph, we can see what the output value is. So here for this input value, I have this output value. And here for this input value, I have a different output value. But notice that there are several input values, this one and this one, that have the same output value here. Okay. So are these functions? Well, the first one, yes, it's a function. Okay. So we have that for each input value, we only get one output value. And we can see that by taking these vertical cuts or rays. And if the graph only ever is crossed once by this ray or cut, it is a function. Okay, so one input value only maps to one output value. Okay. We'll see later how to use the horizontal rays. So the next one is 2 to the x, a function. Yes, it is a function. Is f of x equal to root x for all real numbers? And the answer is, well, it does map to just one output value, but can we cope with all real numbers? Can we take the square root of a negative number? And the answer is, for real numbers anyway, no. So is this a function? Well, the formula is fine, but the input sets are not. We should really restrict this to real numbers greater than or equal to 0. So if we try to put negative numbers in here, we're going to have a problem. We're not going to be able to cope with those values in the domain. So for that reason, this is not a function. Okay. So we can't square root a negative number, and we're saying that we're allowed negative numbers. Now, if you try to get around this by saying, okay, let f of x be plus or minus the square root of a number. Actually, it doesn't get around it because we still have square root of negative numbers. Okay, so now we take x being greater than or equal to 0. If we take plus or minus the square root of any of those numbers, is that a function? Well, no, because we're saying for one value, let's say 4, we're getting 2 outputs, plus and minus root 4, plus or minus 2. So that is not a function. Okay. Had we said f of x equals plus root of x, or had we said f of x equals minus root of x, restricting the domain, that would have been a function. But can you see here, for this input value, I have that output value and this output value. So if you take a vertical ray, it crosses the curve twice. And so the plus or minus square root of x, which is what this curve represents, is not a function. Okay, we have to decide which one we want. Okay, while functions permit an input only to be mapped to one output, there's nothing stopping multiple inputs mapping to the same output. Okay, and that's called a many-to-one function. So if you've got 2 values going to the same value, that's fine. So for example, f of x equals x squared is a function. Okay, it takes a value 2 to only one value. It takes a value minus 2 to only one value. It copes with both of these values and can cope with any other value you give it. So it's a function. So a function must not send one value to 2 values, but it can send 2 values to one value. And if it is, it's a many-to-one mapping, and because it's a function, it's a many-to-one function. Okay. The other option is it could be a one-to-one function, which basically means that one value in the input set goes to one value in the output set, and every value in the output set corresponds to one value in the input set. This is important for inverses later. Okay. So taking vertical rays tells us whether something is a function. Taking horizontal rays or cuts tells us whether it's many-to-one or one-to-one. Okay. So this function here is one-to-one, means that when we make horizontal cuts, it only ever crosses the curve once. Whereas this one here, y equals x squared, can you see when x equals 2 or when x equals minus 2, we get the output 4. So the output 4 comes from two possible inputs. So this is a function, but it's a many-to-one function. So it still works as a function. The problem is when we want to work out an inverse, we can't have it being a many-to-one function. It will have to be a one-to-one function. But for now, many-to-one functions are fine. So further examples. So you want to go to sketch stuff. So for example, for A, if you want to find the range of these, then the range of f of x equals 3x minus 2 when we put in 1, 2, 3, and 4 is that when you put in 1, you get 1. When you put in 2, you get 4. When you put in 3, you get 7. When you put in 4, you get 10. And so the output set is 1, 4, 7, 10. And you give a set by putting curly brackets. And notice that the function is one-to-one. Now if you look at g of x equals x squared, and we're allowing values from -5 to 5, then if we sketch that, you get this curve here. Notice that this is not one-to-one, that this is many-to-one. For example, 2, 2 and -2 both go to 4. Okay. And what's the range? Well, even though we're putting values -5 to 5 in there, both of them give you an output of 25. But if you notice that 0 outputs 0, then we can see the output of G is any number from 0 to 25, including 0 and 25. Okay, so that's these values here on the y-axis. They all come out by putting in appropriate values between -5 and 5. But notice we mustn't draw this curve any further because the domain is -5 to 5. So it would be wrong to draw this beyond x equals 5 or beyond x equals -5. Last one, h of x equals 1 over x. So we know that looks like a rectangular hyperbola. We have a shape here and a shape there. But because they're restricting the domain from 0 to 3, not including 0, but including 3, then we get just this part of the curve. And if you look at it, you can see that it's one-to-one. And if you want to look at the range of what comes out, well, when you put in 3, out comes 1/3. When you put any values less than 3, you get all the other values coming out. So the output of this, let's go back, the output of this is h of x is greater than or equal to 1/3, all of these values up here. So the range are all the values that come out, and you give them usually as an inequality. Piecewise functions, so these are interesting. This is where for the domain, which in this case seems to be all the reals, we split it up and we use one formula for part of it and another formula for another. So we're going to use the formula 5 minus 2x as the output when x is less than 1, but we'll use the formula x squared plus 3 when x is greater than or equal to 1. So if we sketch it, we draw y equals x squared plus 3 for this part when x is greater than or equal to 1. And notice we use the filled in circle here to indicate the value 1 is being captured by this formula. And then the value 1 is not captured by this formula, so we put an empty circle for the line 5 minus 2x to indicate that I'm not going to use that formula for the value 1. But all the values to the left of it, we use the formula 5 minus 2x. Okay, so that's the sketch. And then state the range of f of x, where we can see that the range is going to be all values greater than 3, it looks like here. Okay. And then solve f of x equals 19. We draw y equals 19 up here. And then if we solve x squared plus 3 equals 19, it has two solutions, but only one of them is valid because we could only use the formula x squared plus 3 for x greater than or equal to 1. So the x equals 4 is fine, but the x equals minus 4 would have crossed the quadratic if we'd drawn it beyond its domain, but we mustn't draw it beyond its domain, and so the -4 solution is not appropriate. It would be wrong. And then for this part here, we need to solve 5 minus 2x equals 19, which gives you x is -7, and that is in the domain of this formula, so that solution is fine. So the two solutions of f of x equals 19 are not 4 and -4, they are 4 and -7, where the 19 crosses the part of the quadratic and where the 19 crosses the straight line, the y equals 19 line, I mean. Okay. And then you can, of course, draw some other stuff. E to the x plus 2, you should know what that looks like. You should be able to write its range. A function like a quadratic, you should be able to draw, and then you should be able to work out what its range is for the particular domain they have here. Be very careful when you're drawing a curve that you do not draw it outside of its domain. So here, x is any real. You can draw something to represent all inputs, but here, x is any real, but x is between 0 and 5. You must only draw this between 0 and 5. And in fact, if you want to be precise about it, I would draw a filled-in circle here and a filled-in circle here to indicate that those points are included. And if one of them wasn't, you'd have a little empty circle at the end to indicate that point isn't in the actual graph. Okay, let's move on. So exercise 2b is what to do after that. So domain and ranges. Okay, so if f of x equals x squared, the domain is any real, and that's fine because x squared can cope with any input. What's the range? Well, I hope you agree the range is going to be any values greater than or equal to 0. 0 squared is 0, and you can't get any negatives, so you should be able to get that. And you should, if you draw the graph, you should agree. What about ln of x? Well, ln of x when x is greater than 0 actually gives you the whole of the real number line, okay? Because it's asymptotic to the y-axis, and if you put in values greater than 0, you will get output all real values. Have a look at the graph or try it on Desmos. You should be able to see it. This is a quadratic, and if you complete the square, you get x plus 1 all squared plus 8, and so you get 8 when x is -1, and then it doesn't go below that, so f of x is greater than or equal to 8 for any reals. 1 over x. Notice that we're not putting all real numbers into 1 over x. Why? Because x is 0 would present a problem. This would not be a function if we said x is any real. By saying x is any real but x not equal to 0, it's now a function because we can't cope with 0, so we mustn't put 0 in the domain. So what's the range? Actually, the range is all output values apart from 0. So you'll get positive and negatives, but you don't get 0 coming out. And you should be able to check by drawing or by playing with it that the range of e to the x is greater than 0. And again, we can put any values in. So here, for example, in this example, we've got f of x equals x squared. We know the range of it generally is f of x is greater than or equal to 0. But in this case, if we're putting values from -1 to 4, -1 goes to 1, 4 goes to 16, but 0 goes to 0. So the output is from 0 to 16, not from 1 to 16. So don't just look at the endpoints necessarily. Notice that in between, this graph dips to 0. And so the output is values greater than or equal to 0, but less than or equal to 16. Okay, so I'll leave that notational note for you to have a look at. Composite functions. This is when we apply one function and then another. Be careful to get the notation right. So if you do f and then g, we write it as gf of x. So if you have an expression gf of f of x, take the x and first of all it meets the f and then it meets the g. So the input value works its way from the right to the left. Okay, so gf of x means f first and then g. Be careful to get it the right way around. So here's some examples. What's f of g of 2? Well, from what I said, this means put 2 into g first. Put in 2 into g, we get 4 times 2 is 8, minus 2 is 6. So g now outputs 6, and then we put that 6 into f. Putting 6 in here, we get 6 squared plus 1 is 36 plus 1 is 37. Okay, so g, first of all, takes 2 to 6, and then f takes that 6 to 37. Try to write it in this way if you can. What's f of g of x in general? Well, now we do the same thing, but with the formulas. So g takes x to 4x minus 2. Now this is where you've got to be careful, because f, rather than thinking of this as f of x equals x squared plus 1, think of it as f of input equals input squared plus 1. So if the input is 4x minus 2, then you're going to get 4x minus 2 squared, because the input is 4x minus 2, you're going to get the input squared plus 1. If you then multiply that out, you'll get this as well. What about gf of x? Well, first of all, we put x into f, which means that we get x squared plus 1, and then we put this as an input into g. So if we now look at the formula for g and think of it as g takes the input, whatever it is, to 4 times the input minus 2, we're now going to get 4 times the input minus 2, where the input is x squared plus 1. Okay, and if we multiply that out, you get this different quadratic. They're different. Now here you've got to be careful. This does not mean f of x times f of x. Okay, you might think it does, but it doesn't. When we're doing composition of functions, it means f of x. So we put x into f, and then we put that output into f again. So f takes x to x squared plus 1. And now if our input is x squared plus 1, we get our input squared plus 1. And so we get x squared plus 1 squared plus 1. Solve g of f of x equals 38. Well, first of all, we have to work out what g of f of x is. So g of f of x was 4x squared plus 2. So if you want to know when it's equal to 38, we're going to get 4x squared plus 2 equals 38. We solve that. Okay, easy. So this is composition of functions, where you put the output of one function into another. And you can do the composition of 2 functions, 3 functions, 4 functions. You can go on as long as you like. You can even compose a function with itself, which is what happened here with f of x. Okay, and then we've got some examples here, which I'll let you work your way through. But here we've got f of g of 3. What does that mean? We put 3 into g. So g takes 3 to 3 plus 1 over 2, which is 3 plus 1 is 4 over 2 is 2. And then putting 2 up here, we get 2 times 2 is 4, minus 8 is minus 4, and the modulus of minus 4 is 4. Okay, and you can do the same thing with f of g of x, and you can sketch these things as well. A bit of testing, I'll leave that for you. Exercise 2c. Okay, well, we're nearly there. Inverse functions. Now, you may have done inverse functions at GCSE, and for simple things like f of x equals 2x plus 1, you can just undo that in reverse by subtracting 1 and dividing by 2. But there's a method really that you need to learn for A level, which hopefully they'll do here. What is an inverse function? Well, if a function takes a value from the input set to the output set, the inverse function, written f to the minus 1, this does not mean 1 over f of x, okay? That's called the reciprocal function. So if f were a variable, f to the minus 1 would be 1 over f. But when you put a function, the notation f to the minus 1 means something different than 1 over f. It means the inverse function. You've got to be careful because this can be very confusing. You may have seen it with trig, okay? Sine to the minus 1 of an angle means the inverse of sine. It doesn't mean 1 over sine. And so this is being used in the functional sense, okay? Sometimes it's called arc sine, which means inverse as well. Okay, so that's what an inverse function is. So here, for example, if f takes 4 to 2, the inverse function will take 2 back to 4. And here is how you'd have done it at GCSE, that if, I'll just close something down. So if you multiply by 2 and add 1, to work backwards to get the inverse, you subtract 1 and then divide by 2. And that works for some cases. But what we're going to do is a slightly different process, and that process will consist of 2 steps. One is that we're going to call the output y, so that would be y equals 2x plus 1, and the first step will be changing the subject. So instead of getting y equals, we'll get x equals in terms of y, and then we swap the x and y's round. Okay. Now, why must a function be one-to-one for the inverse to exist? And this is an important point. So a function can be one-to-one or many-to-one. But if it's many-to-one, we're expecting the inverse function to map that one back to many. And that means that it wouldn't be a function. So for a function to have an inverse, it has to be one-to-one. And if it isn't, you'll have to restrict the domain if it's many to one, so it is 1 to 1. Okay. Okay, so this is the process of finding the inverse A-level style. So even though it's easier to do it by GCSE style, let's look how you do it. So first thing you do is you change the subject. So y equals 2x plus 1 becomes x equals y minus 1 over 2 by moving the minus 1 to the side and divide by 2. And then what we do is we swap the x's and y's round. So what, x becomes y becomes x, and then the inverse function is x minus 1 over 2. Okay, so that's the process. So let's find the inverse function for this one. So y equals 3 minus 4x. We change the subject, so we get x equals 3 minus y over 4. We change the x's and y's round, so now y equals 3 minus x over 4, and that y will be the inverse function. Here's a tougher one. Now this is tough because you can't do it GCSE style. Okay, so first of all, the function is x plus 2 over 2x minus 1 for any reals, but notice we can't put in a half, because if we put in a half, we wouldn't be able to get an output, and so that means it wouldn't be a function. So we must avoid x is a half. But in terms of finding the inverse, don't worry about that half. So first of all, we let y equals x plus 2 over 2x minus 1. We now need to make x the subject. How do we do that? We multiply that by the denominator, 2x minus 1. We multiply out. We now collect all the terms that involve x on one side, all the terms that don't involve x on the other side, because we're trying to make x the subject. And so we get, by collecting all the x's on one side, let's say on the left-hand side, we get 2xy, bringing over this x, we get minus x, equals bringing everything else onto the other side, y plus 2. Now we can factorize out the x, and we get x times 2y minus 1 equals y plus 2. And now the last stage, we just divide by this bracket, and we get x equals y plus 2 over 2y minus 1. And then personally, what I do is I say I'm now swapping x and y's round. So now I get y equals x plus 2 over 2x minus 1, and that is the inverse function. Okay. You could also think about the domain, but they're not worried about it here. When you're graphing an inverse, geometrically what's happening is that you reflect in y equals x. In other words, you're swapping the x and y coordinates. So if this is a point 2, 0, you swap the coordinates around, this will be the point 0, 2. If this is the point 3, 2, this will be the point 2, 3. And that act of changing or swapping the x and y coordinates round is the same as reflecting in y equals x. So geometrically, we get the inverse function by swapping the x and y coordinates, which is the same as reflecting in y equals x. And next thing, notice that the domain of your function, the input values of your function, is the range of your inverse function, okay? Because your inverse function has to take things back. So the domain of one of them is the range of the other, okay? So the input set of one of them is the output set of the other, both ways round. So for f, notice that for this function, the domain is values of x greater than or equal to 1, or rather, sorry, greater than 1. That means the range of the inverse is going to be f to the minus 1 of x greater than 1. Okay. And there we've got that they're reflecting y equals x. So here's an example, and this will probably be near the end. So we've got a function here, g of x is the square root of x minus 2, where x is any real, but x is greater than or equal to 2. We need that, so this is a function. This is a one-to-one function, that's great. G of x will be the range. So if we put in lots of values in here, put in 2, we get 0. Put in 3, we get something bigger than 0. And you should hopefully see that g of x is greater than or equal to 0. There's a mistake here, that should be g of x. So because we call this function g, then we should be writing g of x is greater than or equal to 0. Whoever wrote this had a typo. Calculate the inverse function. So what do we do for the inverse function? We let y equal the output. We change the subject, so we're going to square both sides. We get y squared equals x minus 2. Add 2, so x equals y squared plus 2. Now we change the x and y's round, so we get y equals x squared plus 2, and that's our inverse function. Okay. If we sketch both those graphs, so this is the graph of y equals the square root of x minus 2. Notice only for x greater than or equal to 2. Then we draw only the part of this graph that corresponds to the reflection here. So if this was 2, 0, that'll be 0, 2. And then all these points get reflected to those, and we don't draw this part of the graph because this part of the graph didn't exist here. Okay. State the domain of the inverse. Well, the domain and the and range of the inverse will just be the opposites of the domain and range of the original. Okay. So if the domain of the inverse, because it's the range of the original was values greater than or equal to 0, that will be the domain of the inverse. Okay, and because the domain of the original was values greater than or equal to 2, that means the range of the inverse will be values greater than or equal to 2. So notice how that happens. I think I'll let you have a go at that one, testing stuff. Okay. So now the tricky modulus of a function and f of the modulus of a function. So if we work out a function here, this is x minus 3 times x plus 1. Where it's positive, it stays where it is. But where it's negative, where the output is negative, that has to be made positive like we did with straight lines, and it will come up here. What personally I do is I label this part of the curve y equals x minus 3 times x plus 1, and this one here too. But this part of the curve that comes up here will be the negative of that. So this will be y equals minus x minus 3 times x plus 1. So let's just sketch that, and you can see it looks like that. Okay, they haven't labeled each part of the curve, but I would. Now this one is a bit trickier, b. Okay, let's sketch it and let's explain what's going on. So what happens with f of modulus of x is that you get the original curve, x minus 3 times x plus 1, which would have gone down here, dipped, come back up, and then carried on up here. And you draw that for all positive values of x. Okay, so f of modulus of x, when x is 0, when x is 1, when x is 2, when x is 3, it looks just like the original. But when x is negative, you get exactly the same thing as when you had positives. And so you reflect in y equals x. So you draw for positive x all the values that you have of the original function that you would have got for f of x. But when you get to the negative side, you just reflect whatever's to the right of the y-axis onto the left. I may need to explain why that happens, but that is what happens. Okay, I think that's about it. You've got some examples there that you can look at, and you can do further examples, and you can combine transformations. But I think that's all I'll do for now.